Hey there, folks, back here with another video where, as I had mentioned in the last few videos, we're kind of changing gears a little bit. Not entirely, but a little bit. We are, um, in the last few videos, or at least in the last video, we begun to start to study the topic of antiderivatives. And I had mentioned perhaps one or two times that the antiderivative is actually related to a process known as integration, right? And in fact, the two topics are a bit synonymous. If we talk about finding the antiderivative or performing some integration, the two are, like I said, almost the same, or are the same process in just a general description. Specifically, what we're going to find out is the antiderivative of a function is a process or is a value known as an indefinite integral calculation. It's going to be referred to as an indefinite integral, right? And the process of finding that indefinite integral is known as integration, right? There is also going to come about, right, not too far away, the topic of finding a definite integral. And we're going to talk about the definite integral calculation, which is also a process of integration. All of it is related to antiderivatives in the end. We are going to see this entire topic of integration relate itself to the antiderivative calculation. And that's going to develop in our next few sections, all right? Where that is going to develop in terms of interpretation is a calculation for what we think of as being what we call the area trapped within a curve. All right, let me bring up my notes here. Let me get this, bring this over. All right, so I had noted we are going to start talking about integration. Right, that is the topic we are moving into. Right, it is the next chapter in our study, right? It's kind of where we're going to end our semester here, folks. We are not going to get all the way through integration. Integration, we're really only introduced to it here at the end of Calculus 1. It's not until that we return from Calculus 2 where we devote almost half a semester study to finishing up studying the process of integration. We look at a little application when we come back in Calc 2, and we look at some more advanced techniques for calculation. All right, that is reserved for Calculus 2. All we're going to do here really at the end of Calc 1 is introduce ourselves to this topic. If we are familiar with derivatives, we should be familiar with the topic of antiderivatives and their generic interpretation, their algebraic, or what we might think of as their geometric interpretation. All right. And what I open with here is the antiderivative of a function is also known as an indefinite integral calculation. All right. To begin with, the antiderivative is going to be related to this process known as integration. It is when we perform this calculation, we are performing a process known as integration, right? And furthermore, when we think about integration, in general, integration is related to calculating area trapped within a region bounded by a curve, where that curve is described by a function. All right? And where we start our study here of integration is we start our study with the topic of area trapped by a curve. And we open with a rather classic example here, right? If we think of a region bounded by a curve, something other than a linear path, right? When we have linear paths, the calculations geometrically are rather elementary. We don't have to rely upon calculus techniques. When regions are bounded by lines, we can usually calculate those areas using simple geometry. Area of a rectangle, area of a triangle, area of a parallelogram, area of a trapezoid. All of those calculations will come in handy. Area of polygons, right, will be extremely helpful. And we can rely simply on geometry. However, if we take a region, a space, and we consider one of its edges being bounded by a curve, the calculation becomes a calculus topic, right? The calculation becomes rather complex for that area, and to calculate it to some exact degree is going to require calculus, right? Which means in the end, we're going to see is that it's going to require the use of a limit, right? And here's a classical example again. If we move outside of the linear case, the next case for a curve that might be the simplest situation would be the square function, right? Adding just a little bit of curvature, right? We can do that by using the square function. That might be considered the next basic case of curvature outside of being a straight line, right? So we might consider the function f of x equals x squared, and we might consider the area trapped by that curve and the x-axis, right? Happening in two-dimensional space, right? If you've noted, I may have mentioned this before or not, but when we see this blackboard R and it's squared, this is referring to two-dimensional space, the space made up of the xy coordinate system, over values of x, over values along the horizontal axis, the x-axis, from 0 to 10. And here's an illustration of that area down here below. All right, here we have this curve, f of x equals x squared. All right, we can see that curvature happening from 0 to 10 along the x-axis. At 0, it's 0. At 6, we could see that it's going to give us the value of 36. Right? At 8, it would be 64. At 10, it gives us an output up here at 100. At 100. Right? So what we have here in this illustration is the curve from 0 to 10, with its outputs being displayed from 0 to 100, and actually beyond, where what we're interested in is the area that forms below that curve, trapped between the curve here and this x-axis, this area shaded in this light blue color. That happens starting down here at x equal to 0 up to this location where we see this vertical dashed line where x happens to equal the value of 10. In this region, right, we have an area form. And to calculate that area can be a rather complex calculation, right? To calculate it to some exact degree. We aren't going to be able to rely solely upon geometry, right? We are going to have to bring in the end, we're going to find the use of a limit. All right? But to get to there, we do consider just some approximation techniques that we can use to begin developing, right, the calculation that we see where the limit applies itself. All right? So if we consider approximating this area, right, the technique involves, right, forming a Riemann summation. And to introduce a Riemann summation, right, we might note that the area, right, of the shaded region, we might first of all call it the value of R, right? We'll refer to it as cap R here. We'll put it in an italices formed here, right? So we can kind of see that this is the specific region we're talking about. R being this region here, and R describing the area of this region. What we can note about that region R is it's certainly bigger than 0 units squared. It certainly exists, right? It's greater than nothing. We know that. And likewise, we also know that it's smaller than 1,000 units squared. And you might be saying, well, how do you know that? And I say, well, because that space will fit itself into a rectangle that has a base measurement of 10 units from 0 to 10 and a height, right, of 100 units, right? The output of the function at 10. And in fact, if I scroll down, we'll see an illustration of this rectangle superimposed over our region R. And what we notice is that region R certainly fits within that rectangle, where if we think about the base measurement, it is 10 units, and the height measurement is 100. So 10 times 100 yields 1,000 units squared. So R, right, the area that we're interested in certainly is somewhere between a 0 and 1,000 units squared. All right, we begin there. Now, we can refine that approximation. That is certainly extremely rough. That leaves a lot of variable in that approximation. And we could probably make it a little bit more refined. And the way we could go about doing that is using more subregions of the space. Instead of thinking about one rectangle to approximate this region R, we could consider using multiple rectangles, right, whose dimensions are determined by the function f and that space of x from 0 to 10 along our x-axis, and the number of rectangles that we happen to use. All right. What I do consider doing here in our notes, all right, is I say, well, let's consider using 5 rectangular subregions. All right. Let's subdivide this space R into 5 subregions. If we were to do that, that space might be subdivided as follows here. Right? If we were to use equally sized subregions, right, for example, equally sized subregions along, we should say, the x-axis, subintervals along the x-axis, cutting this into 5 subintervals from 0 to 10, each of those subintervals would be 2 units in length. Right? So if we think about a rectangle forming over each of those subintervals that are 2 units in length, we could make those rectangles have a height determined by the x values that form on the right side of those subintervals. We might think of this first rectangle having a height at an x value of 2. So it would have a very small height of 4. Whereas 4 would have a height of 16, 6 would have a height of 36, 8 would have a height of 64, and 10, this rectangle here with the right endpoint at 10, would have a height of 100. And if we take those equally sized base measurements of 2 units and we multiply them by their individual heights at those values of the right endpoints, at 2 and 4 and 6 and 8 and 10, and we square those values, right, to get 4, 16, 36, 8, and 100, and consider using those in the calculation of our value of R, excuse me, we might say that R here, that region that we're interested in, is certainly going to fit, right, within the area formed by these 5 right triangles. And if we add up that area, it's going to be 8 plus 32 plus 72 plus 128 plus 200. And if we sum up those 5 products, we end up with the value of 440 units squared. So to begin with, we know r is bigger than 0 now and smaller than 440 units squared. All right. What we have forming here is a Riemann summation. Right? This is actually going to be known as a right Riemann sum. Right? It's a right Riemann sum because it's going to use the right endpoints for each of these 5 intervals to help us calculate these values of 4, 16, 36, 64, and 100. What we would note is we could also calculate what might be referred to as a left Riemann sum. In the case for a left Riemann sum, we would use the left endpoints of each of these subintervals. Now, if we were to perform that calculation in this case, using the left endpoints, right, we would have a calculation that I follow up with here, right, where the area in those rectangles would be the area seen here in this illustration, where that first rectangle actually wouldn't exist at all. Right? It would have a length or a base of 2 units but a height of nothing if we use 0 as its measure for the height. Up here, initially, we would have 2 times 0 squared. So that would be 2 times 0, and 2 times 0 is 0. Right? So 0 plus this quantity would be just that quantity. And we could ignore the fact that we're adding 0. So this calculation will turn into a sum of 4 values, where the first value will be 2 times the height at 4, a height of 4, right? The height given at the left endpoint at 2, plus 2 times the height at the left endpoint at 4, times plus 2 times the height at the left endpoint at 6, and so forth at 8. We don't work it for 10 because 10 is the rightmost endpoint for the 5th subinterval, and we only consider these values in our calculation. And what we end up seeing is that r must be bigger than 240 units squared. If we add up these 4 products, we will get 240 units squared, and that region we're interested in, we can certainly see has that region we just approximated fit within it. R is bigger than that region. Where above, we saw that region was actually, R was smaller than that 440 units squared. So overall, using 5 subintervals on a left or right Riemann sum, right, we know that that trapped area from 0 to 10 using 5 subintervals is somewhere between 240 and 440 units squared. Right? If we wanted just to use an average of those and say it was about 340 units, well, we would be pretty close to the actual value, I would tell you. Right? In fact, if I was to tell you the actual value is about 333.33 repeating units squared. It's 1,000 units cut by a third. Right? Units squared exactly. Now, how I know that is because I've performed the calculus. But what we start to see is this approximation technique is getting us really close to that value. As I said, if we just average 240 with 440, finding the exact middle between those, we'd be at 340. We'd be off by, what, a little over 6 units. 6.66666 units, to be precise. So we're getting a lot closer to the exact value just by using 5 subintervals in our approximation. And what this approximation on the left-hand side is called is a left Riemann sum. And what this approximation on the right-hand side is called is a right Riemann sum, because they use the left and the right endpoints of these subintervals that formed when we subdivided the interval from 0 to 10 into 5 subintervals. Right? we used 0, 2, 4, 6, and 8 when calculating this left Riemann sum, whereas we used these right endpoints 2, 4, 6, 8, and 10 when we calculated this right Riemann sum. All right. That's what I follow with here in this note. If we were to go on to actually define a Riemann sum, this is what we say in terms of its definition. All right. And there are 3 cases for that Riemann summation. All right. I had to make some quick corrections here, folks. Yeah, a couple little things just to clean this definition up a little bit here. Defining a Riemann summation, first of all, we do have to assume f is continuous over our values of x in the interval from a to b, right? The Riemann summation for our function y equals f of x using n subintervals, right? This is going to be a control point, n. We're going to be able to determine how many subintervals we use in our approximation. In our previous example, we used 5 subintervals, but we could consider the case for 10 or 20 or 100 subintervals. Now, certainly you're going to be adding up then 10 or 20 or 100 terms in your summation. All right. That is because the Riemann summation given for n subintervals over x in the closed interval from a to b is given by this, what we would denote is as a summation, right? This is a summation of, if we actually, for those of you who aren't as familiar with summations, a repetitive calculation that happens with a pattern, that pattern being that the k value in this calculation will cycle from starting at the value of k equal to 1, k is being called the index. The index will cycle from 1 up to the value of n, whatever you happen to set for your number of subintervals. In this case, it would be f at x sub 1, and that would all be times by what would be del x, right? Delta x. And that would be added to that quantity at x2, and that would be added to that quantity at x3, continuing all the way up to ... the final quantity that would be happening at x sub n. All right? Where you see in the summation, right? The terms of this summation are made up of this value of f, the value of our function f, add a value of x that we give a subscript to, x1, x2, x3. That's referred to in general just as x sub k. And this is all multiplied by this quantity referred to as delta x, del x, or delta x. Right? What we note about these quantities, delta x and x sub k, from this general form, is that delta x, is the width of each kth subinterval. It's the actual width of the subintervals determined by the number of subintervals we have and the interval that we are subdividing from A to B. All right? It is calculated by taking the overall length of that subinterval, taking the value of B and subtracting A, and dividing it by n, the number of subintervals we choose to use in our calculation. All right? B minus A divided by n is going to give me the value of delta x, which is going to be the width of each subinterval. And x sub k, this value x sub k that we use inside of our function as an output, as this independent value, is a value of x that happens to exist in this kth subinterval. It's just a generic way of saying a value of x in the kth subinterval. This is a value of x in the first subinterval. This is a value of x in the second subinterval. This is a value of x in the third subinterval. This is a value of x in the nth subinterval. Where you can use any value of x you want. However, if you want to algorithmically develop a technique for calculating those x dependent upon k, you can use a couple of specific values of x sub k. All right. The first value you could use for x sub k, and that's what I give down below here in these three cases, is what's going to give you the x sub k's you're going to see in a left Riemann sum. Depending on what x sub k you use will determine the type of Riemann sum you have, the direction of your Riemann sum, or really technically the type. All right. If we're talking a left Riemann sum, x sub k is going to be your a value, your leftmost bound on your interval that you're subdividing, added to the quantity k minus 1 times the width of your k subinterval times delta x. Whereas if you're going to use the x sub k given by the rightmost endpoint, given by a right Riemann sum, you're going to use x sub k values that start at a, and add to them k plus delta x. All right. These are actually you might say, the easiest to recall or to apply algorithmically is the case for a right Riemann sum. And to show you that you can use other cases beyond just left and right Riemann sums, there's also what's known as a midpoint Riemann sum. And that's when you use the midpoint of the kth subinterval, the x value found in the midpoint of the kth subinterval. And you can calculate that algorithmically by taking the leftmost bound a from this subinterval from a to b, and adding to that the quantity k minus 1/2 times that quantity del x. Now we saw examples using left and Riemann sums above using these values seen here for x sub k. If we relate back to at least one of them, I think I relate back to the right Riemann sum here. As I said, those are usually the easiest to relate to. We had noted the right Riemann sum was given by this calculation above here, where we got 440 units. Now, where this developed from by the definition above was this calculation seen here. Where to begin with, you always start by calculating delta x. You always have to know how wide is each of your subintervals. What are you going to have for the base measurement of each of these rectangles? That's where you start your calculation. That is going to be 10 minus 0 divided by 5 in the case for 5 subintervals. We take the difference of these bounds and divide by the number of subintervals. That gives us the length of 2 for delta x. And x sub k, if we're going to use a right Riemann sum, from the algorithmic formula above, it's going to be my a value. Well, that is 0 in this case, plus k times that value at delta x. And now that's again why you start with delta x. You need to know the width of those subintervals to figure out what is going to be the rightmost bound. All right. So x sub k ends up becoming, in this case, 2 times k. Where if you now substitute that into your function f of x equal to x squared and find f at x sub k, you're going to be finding f at 2k, which is going to be like finding the quantity 2k, and I should be careful here with that squared. That should be technically on the outside here. The quantity 2k squared, which would result in 4 times k squared. In quantity, all right, substituting in 2k into this function here for x, for this value x seen here, we'll substitute it in here and result in 4k squared for this quantity f at x sub k. And our right Riemann sum, if we use the setup given by the definition, will be the summation that starts at k equal to 1 and runs to 5 for f of x sub k times delta x, which is going to be really the summation from k equals 1 to 5, for 4 times k squared times 2. 4k squared being the value f at x sub k, 2 being the value of delta x. Now the 4 times the 2 will simplify to 8, and what you'll be technically summing is the quantity 8k squared. Starting at k equal to 1 in the pattern, and continuing up to k equal to 5 in the pattern. Now in this pattern, then, it would be 8 times 1 squared, plus 8 times 2 squared, plus 8 times 3 squared, plus 8 times 4 squared, going all the way up to k equal to 5, 8 times 5 squared. Now 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So this will all be equal to 8 plus 8 times 4 plus 8 times 9 plus 8 times 16 plus 8 times 25. Where when I multiply out those quantities, you should see some familiar values. You should see 8 plus 32 plus 72 plus 128 plus 200. Where you'll notice those are the products given here in this summation. And what do we note those add up to? Well, those add up to 440 units squared. Right? And that was performing that right Riemann summation by definition. All right? By definition, you get a slight variation in the calculation because through simplification of your formulation here, you can write an argument of k that is a little different than our initial formula. Right? This one just really exploited the fact that the argument f sub k in each of these examples up above here all involved a common factor at 2. I could factor a 2 out of each of these. Right? And that's what, really I could factor out a factor of what? Not just 2, 4. I could factor out a factor of 4 from each of those. And that's what it does. It factors out a 4 from here and leaves 2 times 1, or sorry, leaves 4 times 2, which is 8, times 1. 8 times 1 is 8. That's where we get this 8 from. Factor a 4 out of here, that makes this 2 into an 8 times 4. And down the line here. Right? But that is the formulation for a right Riemann sum. All right? Now, as for calculating this Riemann summation for quite a few number of subintervals, for a large number of subintervals, we might make use of some summation rules, right? We might find those rules a little bit helpful, and there are some that we can use here. Let's take note of the following rules. These are going to help us calculate these formulations when we have quite a few subintervals, right? This wasn't too bad above for 5 subintervals. We had to find 5 products and add them up. But if we had to do this for 100 subintervals, I would not want to find 100 products and then form 100 sums. Well, add up 100 terms, I should say. Right? So there are some rules of summations that make summations a little easier in their patterns. Right? First of all, we're going to let n be greater than 0, and it's going to represent an integer value. It's going to be our number of subintervals in our examples, and c be any constant value, right? We're also going to let a sub k and b sub k just be the arguments of a summation, right? Just be generic arguments, and we're going to need 2 different arguments, right, So we have one that's called a sub k and we have one that's called b sub k. All right? And they both have an index of k, right? The index that's going to match our summation. Well, the first rule here says that if you sum up from k equals 1 up through the nth term, just a constant value, well, that's equal to the constant times n. So if I take a constant of 2 and I sum it from 1 to 10, basically summing 2 10 times. 2 10 times is 2 times 10. 2 times 10 is 20, and that's what this formulation yields. All right? It would be our constant 2 times our number of times it's added together, 10 times. 2 times 10 would yield 20 in value. All right? That's this first summation rule. Here's a second summation rule. It says basically a summation will distribute itself across a sum or difference. If you have two arguments of a summation, a sub k and b sub k, and they're being added together, added or subtracted with one another, that summation will distribute itself across that sum or difference. And you'll end up with the sum or difference of a sum of the sums of the individual arguments. All right? So if you have a multivariable argument, multi-termed argument of a summation, you can consider just adding up the summations for the individual terms of that argument. All right? Now, if you have an argument of a summation times a constant, you can take the argument or the constant times that argument and factor it out of the summation and make it a constant times the summation of just the argument. Right? Constants in a summation will factor themselves out of the summation. Right? Technically, I could have factored out of the summation the value of c and considered just summing up c, or the number 1, 10 times. Well, 1 added to itself 10 times is just the value of 10, and then multiplied by that 2 value for c. 2 times 10 is again 20. It's using that constant multiple rule. Now here's an interesting rule. These are the ones that are going to be a little bit more helpful to us, at least for some polynomial forms. The summation from k equals 1 to n for just k, right? For just the index of k, that actually can be written as a formula in terms of the number of times n occurs. It is n times n plus 1 all divided by 2. So if I add the number, well, the index k 10 times, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 would be what we're adding. Well, that is just going to be 10 times 11, which is 110, divided by 2. It's just going to be 55. So if I add 1 plus 2 plus 3 plus 4 all the way up to 10, that's just going to be 10 times 11 divided by 2. It's going to be 55 in value, which is what this formula gives me. All right. If I was to do that with k squared, take my index and square it each time. All right. 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus what? 64 plus 81 plus 100. Right? There I was summing from k equals 1 to 10 for k squared. Going from 1 squared to 2 squared to 3 squared all the way up to 10 squared, adding up those numbers. Well, to add up those 10 values, they're equivalent to 10 times 11 times 21, all divided by 6 in value. Right? That's going to be the value of adding up those first 10 squares. And we have a third formula for cubes. For cubes, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, all the way up through maybe 10 cubed. That would be when n is 10. Well, that would be 10 squared times 11 squared, all divided by 4 in value. Right? We have these respective formulas. And I can use these in our previous case. Particularly, I can use this formula here we're going to see. Right? Let me show you. Consider again the right Riemann sum for f of x equal to x squared over values of x in the interval from 0 to 10 using 100 subintervals. To begin with, what you have to do is completely redo the calculation. You are going to have to calculate delta x first. In this case, delta x is going to be 10 minus 0 again, but now divided by 100. Instead of each subinterval being 2 units in length, it's now going to be 1/10 of a unit in length because we're using far more subintervals. We're using 20 times as many. So 2 cut by a 20th is 1/10. All right? Each subinterval is now 1/10 of a unit in size. All right? And that means if we think about the rightmost endpoints of each subinterval, well, they are going to be given by a plus k times delta x, so they are going to be given by 0 plus 1/10, my delta x times k, or 1/10 of k. A, 0, coming from this leftmost bound on our interval. That means each of our right bounds are going to be given by a multiple of 1/10 of k. The first one at k equal to 1, the second at 2, the third at 3, and so forth, all the way up to 100. The 100th one would be at 100 divided by 10. Well, what's 100 divided by 10? That's going to be at 10, the rightmost bound. All right. This is how we're going to get the rightmost endpoints on each of these 100 subintervals when we subdivide 0 to 10 into 100 subintervals. This is going to be the algorithmic process for calculating those rightmost endpoints. Now, if we substitute those into our function, the next step, 1/10 substituted into the function where x is being squared will yield 1/10 of k squared. And squaring the 1/10 will yield 1/100th, and squaring the k will yield k squared, and we'll have 1/100th times k squared for f at x sub k. And if we form the calculation of the right Riemann sum, it's going to be given by this formulation seen here. It is going to be the summation from k equals 1 to 100 for f at x sub k times delta x, where f of x sub k above is 1/100th of k squared, and delta x is 1/10. That's off the screen. That's right there. That's 1/10 in value. We substitute that in. Now 1/10 can be multiplied by 1/100th, and they're both constant multiples. So that result of 1/1000th as their product can be factored out as a constant multiple. And you can see here what we're left with. We're left with 1/1000th times the sum from k equals 1 to 100 for k squared. Where we wouldn't necessarily want to add up 1 through 100 being squared. It takes a little bit of time. To be an understatement there for little. What we would consider doing is using the formulation above that says if this n value is 100, then this is going to be 100 times 101 times 201, all divided by 6. All right. So if we bring that formulation in the picture, yeah, this is going to be 1/1000th of n 100 times n plus 1, 101, times 2 times 100 plus 1, 201, all divided by 6. And if you perform the calculation and simplify, you will get the rational form 6,767 divided by 20, which does equal exactly 338.35, right, in value. And if we're using that to approximate that area, right, we should say that is approximately, right, we should probably say here, thus, R is approximately 338.35 units squared. Right? And we can note the following illustration, right, using 100 subintervals. I went ahead and went with just an approximation here. We certainly know it's going to be a little less than that, but it's close to it. And if we take note, what did I say it was? It was about, well, it is exactly 333 1/3. So we're still off by about 5 1/3, a little more than that. In fact, our approximations using the left and the right Riemann sum and averaging those two got us just about as close, and without the formula would have been a little less work. But if I was to continue this approximation off to the 1,000th degree, right, I could certainly refine this calculation considerably. All right. Now, I don't believe I do that. Instead, I do another example. And we could always look at this calculation to the 1,000th degree after we consider this example. Because what I want to show you is you can do this calculation on your calculator. All right. So what we consider calculating here is a Riemann sum. We're going to do it again. This time for the function f of x equals the sine x. Because notice, this calculation works nice above. Right? When we were dealing with an argument of our summation that was in the form k squared, and we only have formulations for the case of k, k squared, and k cubed. For any other argument of k, this isn't really going to be very helpful for a large number of subintervals. So in the technological age, what we have is the use of a graphing calculator. All right. So I consider another example here where I'm going to show you a graphing calculator. And we might consider the calculation above in the end where we maybe perform it on a graphing calculator also, just to double check our process. All right. But here we might consider the right Riemann sum for approximating the area trapped by the sine function. Now we all know what the sine function looks like, right? That's sine wave. Where here we're interested in that approximation just from 0 to pi. So just the area in that first section, half of the period, right? For where the graph is above the horizontal axis. And let's consider doing this with 50 subintervals. All right. Well, to begin with, delta x is going to be pi minus 0 divided by 50. So delta x is going to be basically pi divided by 50. And x sub k, using 0 as our leftmost bound, will be just k times pi over 50. It'll be k times pi divided by 50, right, in its value. And if we substitute that into our function, f of x, that would be just the sine at k times pi divided by 50. And the right Riemann sum, right, using 50 subintervals, would be given by the summation from k equals 1 to 50 for pi divided by 50 times the sine of k times pi divided by 50. Where we don't have rules that help us simplify that. Now, we could technically, I guess, factor out the pi divided by 50. Right? We could technically factor that out as a constant multiple. However, we're still left with summing up 50 times the sine of k times pi divided by 50, where only in probably a few cases are we going to encounter exact values that we can find. Otherwise, we're going to have to rely on decimal approximations, where our calculator will actually do the summation for us. Now let me return this to the original form, because that's how I have it. And what we'll note is on our calculator, right, a TI calculator, you're going to want to go underneath the list menu. All right, let me bring up the calculator here and show you this. Right. You can see on my calculator, you're going to want to go underneath the list menu. Now, where the list menu is right above stat, right next to the left cursor. Right above stat is the second option is the list menu. If I turn my calculator on, I'll go ahead and clear the screen. You can see I've been practicing. We're going to go second list. And underneath the list menu, you're going to see the two options we want. We are going to want to, what we say is sum a sequence. Over here in my notes, we're going to want to sum a sequence. All right? So to sum a sequence, underneath this calculator options, we're going to go over, first of all, to math, and you'll see the fifth option down under math is sum. And then we're going to go back to second stat to open up the list and go over to ops now. And you'll see the fifth option down on the ops menu is sequence. So we're going to grab it and we're going to sum a sequence. Now that's all underneath the list menu. Second list. Underneath the math menu, you'll find sum. And underneath the ops menu, you'll find sequence. Right? Both is option 5. So the sequence we're going to sum, as we set this up, is it is going to be pi divided by 50. And we're going to multiply that by the sine. Now, one thing I didn't check. Let's go back and double check this. Notice our mode, because we are using a trig function and we are talking pi, is referring to radians. So we're going to double check it's set in radians before we go any further. And it is. So it's going to be pi over 50 times the sine of what is going to be, we can see here, k times pi divided by 50. So to get k, I can always use x, but let's be specific here. To do k, we can do alpha, and you can use the alpha command. We're going to take that times 50, and we're going to divide that by pi. And that's going to be the argument of the sine. And now we're going to follow that with the variable that's going to be summed. So again, we're going to select k. That's going to follow with the lower bound on our index 1. And I'll scroll down here in my notes. You can see I give you the command to put in here. What you put into this is, it's first of all, you put in the function, which we just did. That follows up with the variable of interest that you're going to sum. We're going to sum up the variable k. We're going to sum starting at the lower bound of 1, going up through 50, and we're going to increase by 1. The last number is how much we increase by. Sequences can go up by 1, or they can go up by halves, or they can go up by tenths. Here in a Riemann sum, they increase by 1 each time. So we're going to increase by 1. So I'm putting those options in here. We're going to start at 1 on our calculator, separate that by ending at 50 with a comma. We'll separate that by ending counting by 1, and then you need a double ending parentheses. We hit enter. It takes a little while. Oh, that doesn't seem right. Where did I go wrong? Why doesn't that seem right? 1 to 50 by 1, pi over 50 times the sine of k times... Oh! Can you see my error? It's a heck of an error. Let me go fix this. You probably saw it before I put it in there. I know I'm wrong because if we're above the x-axis, we should have a positive area right here. This should be not 50 divided by pi. It should be pi divided by 50. Now, because it's the same number of characters, that's not going to change anything. We hit enter, and now it's going to be correct. 1.999341983. All right. It's almost 2 units. Exactly. If I was to tell you the exact answer, it's exactly 2 units, which is kind of interesting. And as we get further into the study here of integration, I'm going to show you how we calculate that exactly. But this is a pretty good approximation of that using 50 subintervals. All right. So if we bring that result into play, we just note the calculator will yield the following approximation, right? Approximately 1.9999 units squared for that area. Right? The area within the first wave of the sine function using 50 subintervals of that interval from 0 to pi. All right? It's using our calculator to do that calculation. If we were to go back and use our calculator to do the previous example, just to show you that we are right on our process, our calculator should also give you this result if we perform it here. Right? Technically, I should be able to put this into my calculator. Let me show you how to do that. Right? I mean, I could put into my calculator, bring out that constant multiple of 1/1000th, and then just times that by, it would be second list, go over to math, select sum, go back to second list, go over to ops, select sequence, and then what are we summing? We're just summing here now k squared, starting at the value of k, summing over variables of k, the index is k, starting at 1, going up through here, we did 100, my apologies, and we increase by 1 each time. So if we're doing the process right, we should get 338.5 here, or 0.35 here. And we do. All right. If we want to see a little bit more accuracy, let's increase it to 1,000. All we have to do is go back here and let's make that number 1,000. Takes a little while. Still calculating. Oh, we're outside of dimensions. Did it just go too far? Was using 1,000 pushing the limit? I think it might have been. Something is messed up there, right? That doesn't seem right. Oh, you know what it is? What did I not do? I didn't redefine the problem. Remember, if we're going to do this for 1,000 subintervals, we have to redefine our delta x. All right? So just because we're here and we're talking about it, I'm not going to leave you hanging on that. All right? Just to show you we're on the right track for approximating this. Right? If we do 1,000 subintervals, right, for that example, del x is going to equal 10 minus 0 divided by 1,000, right? Because we're approximating it from 0 to 10 using 1,000 subintervals. So that is going to equal a delta x equal to 1/100th, right? X sub k then is going to be my value of a, which is 0, plus k times my delta x value, 1/100. That is going to equal k divided by 100. All right. So for my function f at x sub k, this is going to be f at k divided by 100. And because we're using the square function, this is going to be k squared divided by 100 squared. Right? What's 100 squared? Well, isn't that 10,000? Yeah. So that's 1/10,000th times k squared. So yeah, we're getting quite a bit of ways from where we were having accuracy. We weren't setting the problem up right. So our Riemann summation here, if we consider summing from k equals 1 to 1,000 for f of x sub k times r del x, right? This is going to equal the summation from k equals 1 to 1,000 for the quantity given by 1/10,000th k squared times delta x 1/100th. Let me separate those two groups. This is f of x sub k. This is delta x. And we can see that does simplify. Right? What does that simplify to? We can say that's going to be 1 what was that? 1/1,000,000th? 1/1,000,000th of the summation from k equals 1 to 1,000 for what is just k squared. So let's see if our calculator will do that. And if not, we'll have to go back and change it for 100 here, right? We're going to do second list ops. We're going to sum second list. Oh, sorry, it was math and now it's ops. A sequence, right? 1/1,000,000th times, I'm going to just show you, you can also just use variable x. It'll save you having to write x or k squared. Let's just do it for x squared here. We're going to, for k squared, we're going to use the variable x as our index. We're going to start at 1. We're going to go through 1,000. And we're going to increase by 1 each time. So maybe by bringing that multiple inside too, we've simplified our calculation a little bit. So that the calculator can handle it dimension-wise. Fingers crossed. Oh, failure again. My apologies. My apologies. It's this, probably this older emulator. What would that give me? 1/50th? 50. We would have this over 50k. If we substituted that in here, this is certainly a practice in the formulation. Here we're going to square that. So 50 times 50 is 2,500. $2,500 in here times 1/100th, right? That gives us 250,000. That's certainly a lot smaller. Times the summation. Oh, and I missed that. It only goes up to 500. Oh, man. So let's see here. Two, 5, 0, 0, 0, 0. Delete. We're only going to sum up to 500. Delete. Go back. Make that a 5. Fingers crossed. Can the calculator handle it? Now I'm off again somewhere else in my calculation. You can see I haven't doubled something. 10/50th is 1/50th. No, well, right there. There's my doubling factor. So let's say 50 times 2,500. Oh. Well, duh. And there's going to be my difference. So I'll do second entry again. No, let's not do that entry. Let's do another entry. Next one. That one. So this should be 125. Now that should double everything. Something pretty close to 333.333 repeating. Oh, and we do 334.334 repeating. Close enough. Close enough. Again, using 500 subintervals, there's a little approximation in there. But we're pretty darn close. We're pretty darn close, folks. All right. But yeah, we're at an hour here just playing around at the end, and I wouldn't say wasting your time, but certainly showing you how the calculator is going to help you with doing some approximation techniques, calculating these Riemann sums. However, we're not going to spend a lot of time there. Where we're actually going to get to is the point of being able to do exact calculations. I'm going to show you how to find those calculations exactly. Right? That is going to involve a little bit of the antiderivative. But we're still in the development of that. Where we're heading, folks, is next. We're going to actually see where a limit is going to apply. And you might already start to have the intuition to how you might apply a limit to this argument, to this calculation technique. And then we're going to see how that limit gives us a definition that we're then going to use to help bring about the application of the antiderivative in all this. But like I said, where we're at 110 minutes. So I'm going to end the video there, and I will see you in the next ones to start developing all those ideas. All right, folks. See you then.